see what could come up.
Okay, so in class the other day we started talking about inverse functions, and we were talking about how they undo what an original function does. And so this note sheet starts talking about relations. We actually got more specific with our notes and went right into functions instead of relations. But it's good to kind of wind back and review and get a stronger base. So an inverse of a relation is a relation. So this is in the inverse relations box, and there's a line here. What is the inverse of a relation? It's a relation that reverses or undoes the original relation. And the notation we use for this, for the inverse relation, is r to the negative 1. So this is for inverse relation. So if something is not a function, we can still, we might be able to find an inverse relation if we're using coordinate points. So that would be an example. And then our notation for the inverse function is what again?
F to the negative 1
Nice.
of x.
So these are our two main notations that we'll be using. We'll mostly just be using this one here. And so an example of this, it gives an example of a relation. So I have R, gives me a set of coordinate points, 0, negative 7, negative 1, 2, negative 4, negative 2, 6, and 3. And it's asked me to find the inverse relationship of these coordinate points. What do you guys think that could possibly be? Yes. Switch in the x and y. And why would I do that?
Because that's what math told you to do.
So when I input this value, I get this value, right? When I input the x value into the equation, like I have like f of x equals 2x. The only way I can find a value for the function or a value for y is if I input a number here for x. So I'm inputting a number to get this. Well, the inverse is telling me I have this. How can I work backwards? So it's going the reverse direction. So that would be switching my y and my x in order to solve backwards. Which is, we'll see it when we graph it. It will become a little bit more clear. So this would be 2, negative 1, negative 2, negative 4, and 3, 6. And so this is a great example because this is a y-intercept and this is an x-intercept. So if I was graphing these and I had a point at 0, negative 7, and then I had a point at 7, negative 7, 0, and I had two graphs here, if this was a point on a line here and this was a point on a line here, I would know that these were inverses because they have opposite coordinate points. Okay. And so, based on what we know about inverse functions, does every function have an inverse? No. What does it have to be in order to have an inverse?
Original x and, or not original, unique, that's the word.
Yep.
X and y value.
And what is the term for that? 1 to 1. So 1-to-1 functions are the only functions that have inverses, so only functions with inverses. And just like Annabelle says, they have a unique x and y value. And no repeating, specifically no repeats with my y values. And what is the test we use to discover if it's a 1-to-1? The horizontal line test. So we use the horizontal line test to determine. And why would we use that? What does the horizontal line test for? Yeah, so if I have a parabola here, I have my parent function f of x equals x squared. My horizontal line test would fail because I have two y values that are the same on that line. This would not pass the horizontal line test, and it would not have an inverse.
I have a question.
Yes.
So you know how you were talking about inputting the into decimals and stuff like
Mhm.
that? If we know the parent functions well enough,
Yeah, you don't
Just
need to
go.
use it.
Okay.
Yeah, like I did with the number 4 on there. Like the reciprocal ones are a little bit challenging, especially if there's two variables, like in the top and the bottom, numerator, denominator. But when you have like a linear or a quadratic or a cubic, you're like, I'm fine. I know that this is passing or not passing. Yeah, you're fine.
To determine
To determine if it passes the horizontal line test. So the horizontal line test is used to determine whether the inverse of a relation is a function. And so, like I said here, we're determining what the output is. If I have repeating outputs, then I'm going to get confused on what the original input is. So I can't have two repeating outputs because then, like, how am I going to figure out the original? So what I want you to do is I want you to look at number 1 through 6 on the examples. There's like a linear, there's a sine, there's a reciprocal, there's a cube root, there's a horizontal, it's hard to see on number 5, and then there's a sideways parabola. And I want you to let me know if it passes the 1-to-1. And remember that it also has to pass the vertical line test in order to be a function too. So I just want you to write yes or no if it's a 1-to-1 function for those 6.
Number 5 would be no. Right?
Correct.
Okay.
Because I have, for all my x values, I have the same y value.
You said vertical line test too, right?
Yeah, it has to pass the vertical line test because it has to be a function. So you guys should have yes, no, yes, yes, no, no. So yes, no, yes, yes, no, no for that. Easy enough, right? Can I get a thumbs up, middle, down for drawing a horizontal line through a graph? If it's challenging, please let me know. Don't be upset. We can work on it. Okay. So now it's getting a little more specific, and we're actually talking about the inverse of functions. So this is what we went over in different phrasing than the steps we did in our last class. So we had those 5 steps. What was my first step of those 5 steps? To solve for the
See if
inverse?
it's, a function.
Yeah, so to solve
horizontal.
for x, I have to see if it passes horizontal line test. So this is kind of written in this box here. So the notation, the inverse of a function f of x is written as f to the negative 1 of x. Not all functions have inverse functions, so our first step has to be to see if it passes the horizontal line test. Then our second step is to replace f of x with y. What's my third step?
Interchange x and y.
Yep, swap x and y. What's my fourth step?
So
Nice, solve for y.
right.
And then I swap out y for my inverse function notation. So I want you to do 7, 9, and 13 right now. And if you finish those 3, you can continue on to more. And we'll go over all 3 of those.
Oh, that's actually better.
So swap out x and y and then solve for y. So we have to do x plus 8 and then divided by 4.
Oh yeah.
So you can't get an actual number there because I have two variables. Yeah, or you can just write it down. Thank you. Read at this one. And this one you can simplify a little bit more, but that looks good.
This one we can pass, right?
Right.
Do you want us to do flex?
Yeah, well, yeah. So for this one, you cannot simplify it past this point unless you do 1/4 of x plus 2. Because all you did here is divide 8 by 4. And then you just left x on its own. X is also being divided by 4. Right? So for this one, I'd have to multiply this first one. Oh, you don't remember this yet. So it kind of looks like this.
So it's like the cube.
Yeah, this is the cube root and then this is the
I have
cube
no
root.
idea if
Is this
I'm doing this
13?
right.
Yeah, 13 that looks like this.
So it
I
doesn't
think
count.
leave it as this.
No, it does. It passes. The cubic passes, or the cube root passes.
I'm stuck.
Where are you stuck?
How do I get rid
So
of
you
that?
got rid of it by
Oh, right, yeah.
Yo, Ryan, do you divide out the 4 or do you delete
yes,
it?
to be a function. Yes, that's both.
13.
7.
You just like leave the 4 on the board.
Yeah,
Like
You don't
x plus 4.
you don't divide out the 4. Betty, 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 Betty.
Watch the cord, it's so dangerous. Okay, so if you're not done, that's alright. You can finish up as we can start to go over a few of these. So in number 7, I have a linear equation. So I know that it passes the horizontal line test because it's just going to look something like this, based on my knowledge of transformations and paired functions. So it's going to pass the horizontal line test, and now I can go through all my steps. So replace f of x with y, swap y and x, and then I solve for y. So it becomes x plus 8 equals 4y, x plus 8 over 4 equals y. And then, this is 8. Then I can take this further, or you could leave this as the simplest form. So this could be the simplest form. But if I'm going to be graphing it, I kind of want to get it into something that resembles slope-intercept form. So that way I can have a slope that I can have a point to graph off of. So this would become 1/4 x plus, so that's 1/4 x, plus 8 over 4, which is 2. So you guys can leave it in either form that you want, 8 plus x plus 8 over 4, or 1/4 x plus 2. Either answer I will accept. And then number 9, trying to be tricky, throw this a quadratic, so I have f of x equals x minus 4 squared plus 6. So I know based on my transformations, this is going to look something like 4 to the left, 4 to the right, then up 6. So my graph is going to look like that, but does it pass the horizontal line test?
No.
So no inverse fails HLT would be what I would write.
What about when the absolute value one fail too?
Exactly, yeah. Nice call.
Number 12.
Yep, in number 12 it would also fail. Because I have a vertical stretch there and then a translation of one left, but that still doesn't make it change y values. So we'll see an example that where it's so in the next sheet of notes we'll see an example of how you can make a quadratic fit the vertical line test, and it's by restricting the domain. So like I could say this is x is less than 4 or x is greater than 4, and then it would pass because it would just be carrying these values instead of no repeats. So we'll see how that they can change that up. Get tricky. Alright, so then in number 13, I have a cube root, so that passes. X minus 9 over 4, so it passes HLT, and then I replace y, minus 9 over 4, swap y and x, y minus 9 over 4, and now I solve 4x equals the cube root of y minus 9. Cube both sides, so 4x cubed equals y minus 9. And then I can cube this, so it becomes 64x cubed plus 9 equals y. And then this would be my simplest form. If you left it like 4x cubed plus 9, I would still take it, but this is proper simplest form. Pretty good? Kinda?
Oh,
A little shruggy?
oh,
So this would become 4x cubed plus 9 equals. I'd accept either of these. Okay. So like we're doing these out and we're finding the inverses, but like how do we actually know like that we're doing it right? How do we actually verify that these are actual inverses of each other? Well, there's two ways to verify that they're inverses. The first one that we're going to look at is graphically verifying. So using graphs to verify, is this the right equation? Am I doing this right? Are they actually undoing each other? And so I'm on this sheet now. It says verifying inverses graphically on the top left. And then in this notes examples, what I'm going to write is two functions are inverses if they are reflections of each other in the line y equals x. What does this line y equals x look like? What's my crossing point? What's my x and y intercept here? Well, what do I do to find my y intercept? I plug in what for x? 0. So what would y be?
2.
So
So it's just the x line.
yeah, so the origin is my x and y intercept, and then what's my slope here?
0.
1. So this is my line y equals x. And why do you think I'd use this line as my reflection point? What does it do to my Cartesian graph here? What does it do? It splits up the quadrants, right? So remember here I have my plus plus quadrant, here I have my negative plus quadrant, here I have my negative negative, and here I have my plus negative. So it splits it up so that way if I have a point here on a line, my reflection would be in this plus negative quadrant. So my reflection should be the opposite value. So if I have a point here of negative 2, 2, if I had a reflection over it, and if it was on a line, it would be an inverse if it was at the point 2, negative 2. So I'm using this y equals x line to really split up my Cartesian, my coordinates here, my different quadrants. So that way, like here, if I have a point like on a line and it's 3, 1, here it's going to be -3, -1. So those would not be reflections. These would be. Okay. So how do we actually do this? I'll leave that up there. So I have the function f of x equals 3x minus 6. I'm going to graph my y equals x line with a dotted line there. So I'm going to graph this line, 3x minus 6. My y-intercept is 6. 1, 2, 3. 6 minus 6. And then I have a slope of 3. 1, 2, 3, 1, 2, 3. So looks something 1, 2, 3, something like this. This is not gonna do it the graph justice. You guys are gonna have to graph this on your teeny little graph paper here. So does this line pass the horizontal line test? Yes. So I'm gonna go forward and I'm gonna find my inverse. So y equals 3x minus 6, x equals 3y minus 6, x plus 6 equals 3y. And then I can rewrite this as 1/3 x plus 2. 1/3, 1/3, and then 6 divided by 3 is 2. And so the way I would graph this is I'd go up 2, 1, 2, and then I would use my slope of 1/3 to find out where I'm crossing. So I would cross here. And so how could I figure out if this was a reflection? What could I use here? What are 2 points that I know I have here? Yeah. So I have this point here of 0, 2. I have this point of 0, -6. But I also, if you guys look at where this crosses based on the slope, this is at the point 2, 0 is the x-intercept for this first line. And so these 2 points are good reflection points to show me that if I had done this correctly, it would have had this dotted line going like through the middle like this. You guys know how great I am at sketching. But yeah, so all these points here would have the x and y values reversed on the other side of the line. So like at 0, -6, this point here would be at -6, 0. So it would be a reflection over that y equals x line. So why don't you guys try to do number 2 on your own though? And you can use your graphic calculator if you need to.
I don't get, like, I get graphing it and the like math and stuff, but I don't get, like, why. What are you trying to?
That's a good question. So what I'm trying to figure out here is, do these 2 lines reflect each other? Like, I can go through and I've solved this. We've gone through that, but we want to see, so this point is the reflection of this point. This point is the reflection of this point. So I'm just verifying that the work I did actually works. All I'm doing is, like, I'm telling you, like, solve for the inverse, but, like, how does that actually make sense? Like, how do you actually know I'm not just lying to you?
Sometimes you don't.
Sometimes you just don't know. I do my best to be as honest as possible. So try and do number 2.
what we do when we get stuck with the y to the third.
A y to the third. So how would I get rid of a third power? What would I do to it?
Square root it by the or cube root it.
Nice. Yeah.
So
So is
and then do we graph the cube root?
Yeah.
Okay.
In which step do you root it?
So if this graph passes x cubed plus 4 passes the horizontal line test.
Yeah.
Now I'm going to solve for my inverse. So then I have x equals y cubed plus 4. X minus 4 equals y cubed.
Yeah, I did that.
So now I have to cube root the y to the third in order to get y by itself. So then I would cube root both sides. So the cube root of x minus 4 equals my inverse
I
function.
did x minus 4 to the 1 half.
To the 1/2?
One third.
1/3, that's fine.
We supposed to know where it is.
So for this one, I'm moving my cube root function over to the right by 4. 1, 2, 4. So remember, this one's like really flattish. Like kind of looks like this, and then it curves over like that. And so 2 points that I can use here are at this point 0, 4, and at this point 4, 0. And I can do this without even graphing it, because here I have my y-intercept of 4, and here I have my x-intercept changed to positive 4. Because I'm moving the original function that normally crosses through the origin, I'm moving the point of inflection over to cross at 4 here. And if I was to choose other values like here and here, if I was to solve for those would also be reflections of each other. You can. This is where, like, if this isn't good enough to prove to you that it's like, you may like be looking at it and you're like, I don't actually know, like, especially with the reciprocal graph, it's really difficult to see. Where the trace function on your graphing calculator is like really helpful, because you can like trace down to certain points and see if they are reflections. Okay, so this is graphically verifying that they're inverses. There's also algebraic. So we've been doing a lot of practice with composite functions, and you guys are all loving it. And I see all the smiles and happiness, good times, f of g of x and g of f of x. Whoop, whoop. Thank you. Yeah, whoop, whoop. So exciting. So why have we been doing that? Why have we been practicing that?
So we can
Because
do it.
those are ways we use those methods to verify if functions are inverses of each other. So in this bottom left box, it says verifying inverses algebraically. The definition on the lines there will say two functions are inverses if f of g of x equals x and g of f of x equals x. Make this not look like a multiplication. Pretty cool. Get pumped. We're going to prove this.
So, if f of g of x equals x and O g
And g of f of x equals x, then the two are inverses. So we've been solving our composite functions, and we've been getting something very different than x. We haven't ever gotten x as an answer in our practice problems. But if we were to take both of these and get x as our answer, then we would have an inverse.
How exhilarating.
I know. So if you look at number 3, we have f of x equals to x over 7, or x minus 7 over 2, and we have g of x, wow, these are so vibrant today, equals 2x plus 7. So in order to find out if they're inverses algebraically, I have to now take the composite functions. So I'm going to do f of g of x first. So I'm going to do f of g of x which equals f of 2x plus 7. So this equals 2x plus 7 minus 7 over 2. So that's unsimplified. Now I'm going to start simplifying it. So I can drop these parentheses. What's 7 minus 7? 0. So I have 2x over 2, which equals x. So f of g of x equals x. So we're well on our way now. So now I'm going to solve for g of f of x, which is g of f of x, which also equals g of x minus 7 over 2. So we're going to plug this in for x here. So I have 2 times x minus 7 over 2 plus 7. So what can I do here to simplify this? Instead of distributing the whole thing, which would become 2x minus 14 over 2, what can I do instead? I can cancel out the 2's. It's the same thing as 2 over 1 times this fraction in here, so I can cancel
You cancel out the
numerator
sevens.
and the
Cancel out the sevens.
Yep, so now the 7's cancel out, and I'm just left with x. So this is a pass, and they are inverses. Yay. So number 4 is where I told you it'd start getting tricky, and they're starting to do some domain restrictions on a quadratic function. So we have f of x equal to x squared minus 5. Would this normally pass the horizontal line test?
No.
No, but they put in parentheses if x is greater than or equal to 0.
So now it will.
So now it will pass the horizontal line test because I've taken out the left-hand side of the y values that repeat. And I have g of x equal to the square root of x plus 5. And so when I'm solving this, I'm not even going to reference this. The only thing that I'm going to use that for is does it pass the horizontal line test? And once I say that, then I don't need to worry about this. I don't want to get bogged down with the domain restriction details. I'm not asking you for the domain.
Can't you just look at that though and just know that it's gonna work?
Yeah, so if this wasn't here, I would know it wouldn't because it's parabola, but because that's there, I know it will, and that's good. All right, so I have f of g of x, which equals f of square root of x plus 5, and I'm going to solve for this. So I'm going to put in square root of x plus 5 squared minus 5. So how do I start simplifying this?
The square root and the square cancel out.
Perfect. And then I'm left with x plus 5 minus 5. So those cancel, and I'm just left with x. So f of g of x works. So then I have g of f of x here, which equals g of x squared minus 5. So I'm going to plug in square root x squared minus 5 plus there. Oops, I should reverse those colors. X squared minus 5 plus 5. So what can I do here?
5.
5's cancel, and then I'm left with the square root of x squared.
Which
Those cancel, and I'm just left with x. So that works inverses. Cool. So you guys do number 5. It's a lot trickier. You guys can do number 5, and we'll go over it. What?
Choose number 5.
Well, I want to see how you can do it on your own and then guide you if you have challenges. So we'll go over it together. I'm not leaving you alone with this. I'm just seeing how you can step up.
Wait, this is horrible.
I love fractions. Fractions are just numbers that just want to be pieces of each other.
What's gonna be on the quiz?
Quiz will be I think
Was it
2
this?
piecewise functions questions. It's just everything we've learned since we got back.
So this
Why
thing.
does there have
Yes.
to be piecewise functions on it?
Because. But you can use your notes in your homework, so hopefully that will help.
Which
So the questions will.
Wow, that's just.
So like the questions will.
You plug G in for both X's. You always plug it in for both.
Then we have
So the
like
questions will look
3
similar.
different lines. There's like so
You
many.
do have 3 different lines. That's very true.
How do you do that?
So then you simplify it. You have to find a common denominator for your numerator.
For all
Or
3 of
there's
them.
so many.
No, there isn't. There's only one that you have to find a common denominator for, and that's the numerator. And then you have- And then you have a fraction over a fraction, and then I can set it up as a fraction divided by a fraction, and then flip the
That's
numerator
so
and denominator.
What?
It's hard.
Fractions within a fraction is just like
The best.
why?
It always seems to happen though, so it must be something
Yeah, I'm gonna try to
important.
know how to do it.
All right, so let's go over.
Doing well
Let's
with this,
start it.
Yeah,
Especially.
You guys
this
seem to
killed it.
crushing.
I was on point with weight.
And then we just kept on moving, and my brain it stopped. You know,
All right, so I have
good strong 3/4.
f of x equal to, or f of x is equal to x plus 3 over 2x. Ooh, 2 x's and a fraction. So fun. And then I have g of x equals to 3 over 2x minus 1. Not as fun, only 1x. Whatever. So f of g of x equals f of 3 over 2x minus 1. So what that means is that I'm plugging this in for both of my x values here. So it becomes 3 over 2x minus 1 plus 3, which, what's the denominator on that? What's the denominator for 3? 3 over 1. Over 2 times 3 over 2x minus 1. Okay, so the first thing I need you to address is this really awkward numerator-denominator situation in the numerator. So I have to find a common denominator. So I multiply 3 over 1 by 2x minus 1 over 2x minus 1. You get a common denominator.
Couldn't you just cross out the 2, 3
It's something
x minus 1s and then get 3 over 2 for the answer?
No. Because I'm adding here. So I can't cross anything out because I'm adding.
No, I meant like the top one and the bottom one. The 3 over 2x minus 1.
Still because I'm adding something to it, I can't.
Okay.
If I was multiplying or dividing, I could cancel these.
Okay.
Yeah. So I got 3 over 2x minus 1 plus 6x minus 3 over 2x minus 1. So this becomes 2x minus 1 in my denominator and 6x in my numerator because these 3's cancel. Now I'm going to solve my denominator. So I just get 6 over 2x minus 1. A lot easier. I can rewrite this as 6x over that divided by 6 over 2x minus 1. What can I do now?
Flip it.
Flip it and
Flip it.
multiply it. Yeah.
I'm lost in the sauce.
So these cancel, and the 6's cancel, and I'm left with x. Woo! Boom. That was a lot, right?
Yeah.
That was too much.
Because this is sooner.
So because now that I'm multiplying, I can cancel out these terms. And the 6's, I'm just left with x. So then with g of f of x, g of x plus 3 over 2x, this one's going to be a little quicker, hopefully. This equals 3 over 2 times x plus 3 over 2x minus 1. So this becomes 3 over 2x plus 6 over 2x minus 1. I have to solve for this 1 here. So I can just change this to 2x over 2x. And I'm left with 3 over, so this 2x over 2x, 6 over 2x. And so then I do 3 over 1 divided by 6 over 2x. And I flip it and multiply, so it becomes 2x over 6 times, this becomes 6x over 6. These cancel and I'm left with x. Boom.
What?
Is there gonna be something to fill in the quiz?
Props.
Oh my god.
Like this hard?
Maybe not this hard. So for homework, you guys are going to do 6, 7, 8, and 9, both graphically and algebraically. So what I would suggest doing is solving out for the inverse in the left-hand column. So solving for the inverse here, and then graphing it out here. You can use Desmos or your calculator, and then doing your composite functions in the right-hand column. Only those 4. Realistically, it's 8, but yeah, that's it. It's due the night before your test.